Hello, it's Dr. Harris, and we're back for our last video in covering Chapter 7 material in our Math 111 statistics course. And in this video, we're going to be working with the question about looking at inference for the difference between two population means. So just to recall, we want to distinguish between situations where we're looking for the mean difference, where we have two observations from the same set of data, and we're looking at how the differences between the two observations behave, and the case where we're looking at for the difference of two means, where we have two samples drawn from two separate populations independently, and we calculate a mean for each sample, and then we're looking at the difference between those two sample means and seeing what that says about the difference between the two population means. So we will start by looking at a lot of notation. The notation should be reasonably familiar to us. The main thing is we've got subscripts present to distinguish information that's attached to population 1 and information that's attached to population 2. And so mu1 and mu2 are going to be our population means for populations 1 and 2 respectively. x1 bar and x2 bar are going to be the sample means. N1 and N2 are going to be the sample sizes. And then we've got the population standard deviations, sigma 1 and sigma 2, and the sample standard deviations, S1 and S2. Mu1, mu2, sigma 1, and sigma 2 are unknown. X bar 1, X bar 2, S1, S2, those are the things that we'll be able to calculate from our sample data. And N1 and N2 will be our respective sample sizes. So what we're hoping to do is we're hoping to be able to say interesting, intelligent things about the difference between mu1 and mu2. And so we're looking at mu1 minus mu2. And as I note here, we're going to see about finding a range of values on which we think the value of the population difference is likely to be. That's a confidence interval. And then if we were given a specific value for the difference, typically 0, we're trying to determine if there's a difference between the population means by far the majority of the time. Can we make an assessment of whether or not that hypothesis that the difference between the two population means is 0 is reasonable or not? Will we reject or fail to reject that hypothesis? And so in order to find the confidence interval or to calculate a t-score, we're going to need a value for standard error. And then we're going to talk about degrees of freedom in this case as well. We're going to have t-distributions again. So we've seen this sort of thing back in chapter 6 when we were looking at the difference between two population proportions, that if we just took the standard deviation for one group and added it to the standard deviation to the second group, and then took the square root of that sum, we wound up with what we looked like the standard error in the population proportion case. And we're going to do something very similar here. We know that sigma over the square root of n is the standard deviation for the distribution of x bar when our conditions are met. And so sigma 1 squared over n1 would be what would be underneath the radical if I chose to move that sigma underneath the radical. And so the expression here, sigma 1 squared over n1, that is just the standard deviation, or the square of the standard deviation for a single population 1. This would be the square of the standard deviation for population 2. So we're going to add those two things together and then take the collective square root to get our standard deviation for the distribution of x1 bar minus x2 bar. But since we don't know sigma 1 or sigma 2, we're going to replace them with S1 and S2. And so the standard error formula that we're going to be using in this chapter is the square root of S1 squared over N1 plus S2 squared over N2. What are we going to do about degrees of freedom? Well, R will, if we're turning everything over to R, they will have an internal formula, rather complicated, for calculating degrees of freedom based on the sample sizes N1 and N2. we're going to take something a little more simple. It's going to give us different results than our future one-stop shopping command, but it'll still give us reasonable. It's a reasonable approach if we don't have the technology to calculate degrees of freedom. Um, so let me go ahead and talk about that. We'll move back to this other slide momentarily. So for degrees of freedom, if we're doing things by hand, we're going to use the minimum of n1 minus 1 and n2 minus 1. So we're going to take the one less than the smaller of the two sample sizes. And so as I say here, when our sample sizes are 16 and 23, for instance, we would use 15 degrees of freedom for our estimates. So just to back up before we move on and look at other examples, for confidence intervals, our margin of error formula is going to be t star times our standard error. And for hypothesis testing, our t-score is going to be the difference between the sample means minus the null value, which is often 0. Almost the examples we're going to be looking at, the null value will be 0. So it'll be the difference between the sample means divided by the standard error. And so we're going to have t-distributions running around again. And so, as I said here, if we're doing things by hand, one less than the smaller sample size will be our degrees of freedom that we'll use. And as I said, RStudio will use a more complicated internal formula for coming up with a more accurate result. So we're going to work one example in full, and then I'm going to start you on a second example, and let you finish it up here. So we saw this question back in our first slideshow for this chapter. Do chicks that grow up on a diet containing linseed feed differ in weight from those who grow up on a diet that contains horse bean feed? And so this is question 727 in our text. It's on page 275. Let's go ahead and take a look at that question. Here, I'll blow it up just a little bit. And so the two groups that we're looking at here are the horse bean and linseed groups, the second and third in our list here. And so we're asking, do we detect a difference in the mean weights of chicks that grow up on these two feeds? And so this will come back to these box plots in a couple of minutes, but I just want to give you a chance to read this question a little more carefully if you don't have your book turned to page 275 right now. And so we're going to try to find out if there's a difference in the mean weights of chicks that grow up on these two feeds. So mu1 will be the mean weight of the chicks that grow up on the linseed diet. Mu2 will be the mean weight of the chicks that grow up on the horse bean diet. And so our parameter of interest in this case, once we've described mu1 and mu2 in words, is the difference mu1 minus mu2. Okay, so our hypotheses, if we go back and look at the question, is there a difference? So do they differ in weight? That suggests that we're testing to see if they're the same. Those means are the same or not. So our null hypothesis is going to be that there is no difference between the two. Mu1 minus mu2 equals 0. And our alternative hypothesis will be that there is indeed a difference, that mu1 minus mu2 is not equal to 0. So we want to check and make sure that our conditions are met. So recall that we need to have relatively symmetric distributions, especially if our sample sizes are pretty small. And the way since we don't have density plots here, we only have box plots, we're going to look at the box plots that were there on page 275 to take a closer look. I'm going to go back to that right now. And both the horse bean box plot and the linseed box plot, those are both relatively symmetric. Now the median is not quite exactly in the middle between the two quartiles, but it's not too far away from the middle in either case. And the whiskers aren't equal length, but they're pretty close in length. And so just by looking at the two box plots, we get a sense that we get a sense that they are relatively symmetric in nature, even though the sample sizes are very small, 10 for the horse bean, 12 for the linseed. But so it's the symmetry of the box plots, relative symmetry, that leads us to think that maybe we're okay in proceeding by not having any significant outliers or skew to the distributions. So it looks like it's reasonable to believe that both of these come from bell-shaped distributions. Okay, so we've checked our conditions. The data I've got here on this slide come directly from the table that's to the right of those box plots on page 275. And notice that, again, the numbers that are attached with the subscript 1s are those that go with the linseed diet, and those with the subscript 2 on them come from the horse bean diet. We want to make sure that we're keeping track of which one population 1 is and which one population 2 is. So I've computed the standard error using R this time, square root of 52.24 squared divided by 12 plus 38.63 squared divided by 10. And we get a standard error of just a little more than 19.4. So once we've got that, the next thing to do if we're going to form a confidence interval is to find the value of T star. Our sample sizes are 10 and 12. That means that we're going to have a number of degrees of freedom if we're doing things by hand of 1 less than the smaller one, which is 9. So if I'm going to go here to my T table, 9 degrees of freedom, if I'm going to do a 95% confidence interval, my value of T star is 2.26. And so to find the values for my confidence interval, I'm going to take the difference between the two sample means, and I'm going to subtract from that 2.26 times the standard error and add 2.26 times the standard error, and we get roughly from 14.5 ounces to 102.5 ounces. So we're 95% confident that the difference in mean weights of the chicks raised on these two supplements is between those two numbers, 14.7, 102.4 ounces. So that's our sentence that interprets our confidence interval. If I want to perform a hypothesis test, I need my t-score. Remember, to use PTGC, we're going to compute a t-score. So I've got the difference between my sample means minus the null value, which is 0, divided by the standard error, and I get 3.02. And so our t-score is 3.02. Our p-value is going to be the probability that the t-score would be outside the range negative 3.02 to 3.02. And we get this value, 0.0145 for our p-value. We write a nice sentence that interprets this. If there is no difference in mean weights gained by chicks on the two supplements, that's our null hypothesis stated in words, we would get a sample difference in means as far apart as we did, or farther, about 1.5% of the time. Since that's less than the 5% value that we normally choose for alpha, we're going to reject the null hypothesis. And so we'll conclude that we do have sufficient evidence to say that there is a difference in the weights of chicks that are given the linseed and horse bean supplements. And the evidence also suggests that it looks like the linseed diet is going to result in a higher weight for those chicks. On to one-stop shopping. We get to use t-test GC again in this section, just like we did with a single mean. If we have summary data like we do here, we need to give it the values of the two means, the two standard deviations, the two sample sizes, and the order matters here. So the 218.75, the 15.24, and the 12 all go with the linseed diet. The 160.2, the 38.65, and the 10 all go with the horse bean diet. We'll take our null value to be 0. Our alternative is 2-sided. I could add graph equals true here to get a graph, but we'll see that we get slightly different results. And the reason for that is that we're using a different number of degrees of freedom. The internal computation for degrees of freedom this time was a little under 20. It's going to be a fractional value invariably when the computer is doing the computation for us. So it's using a different value for degrees of freedom that's going to result in a smaller value of T star. Remember, as degrees of freedom goes up, our T star values are going to go down, get closer to the Z star values that we saw earlier in the course. And so we're going to get narrower confidence intervals, and we're also going to get smaller P values. And so our confidence interval is a little narrower. It goes from 18 to 99 this time, and our p-value is below 1%, about 0.7% this time. We'll draw the same conclusions. We'll reject the null hypothesis again, but I just want to point out that with a different number of degrees of freedom, we're going to get slightly different results from t-test GC in this two population case. Now for another example where I'm going to be asking you to do some of the work before we get to class. This is one with preloaded data. Do males and females at Georgetown College differ in the fastest speed that they've ever driven? And so the variable that we're interested in is fastest, out of the M111 survey data set, and then sex. So we'll let the males be population 1 this time. U1 will be the mean fastest speed driven by GC males. U2, the mean fastest speed driven by GC females. And we are looking at mu1 minus mu2, the difference between those two mean speeds. Before we proceed, we should look at our data. We can do density plots. Recall the density plot command when we want to look at a numerical variable broken down by values of the categorical variable. We want to break it down by gender this time, so we'll use the layout equals C1, 2 piece at the end here, and we've got our top and bottom density plots here. The female density plot looks pretty symmetric. It's got maybe a slight right skew to it, and the male density plot definitely has a bit of a right skew, especially with those maybe 2 high outliers that we see there. So we need to be a little bit careful about proceeding. And so maybe this is one of those cases where we should go back and look at the sample size just to make sure that we're good. Favestats will tell us what the sample size was. And so we see that there are 40 women, 31 men. Both are bigger than 30. So with our sample sizes, we're tending to think are probably big enough to overcome the skew that we see, the slight skew we see with the females, and even the outliers that we see in the men's case. So we're going to go ahead and proceed. But notice that we've done checking of our conditions here. Okay, so I'll go ahead and compute the standard error. We can go back to favestats. For this, we've got the means and standard deviations. We use the standard deviations and the sample sizes to come up with the standard error. So it's going to be 22.57 squared over 31 plus 17.61 squared over 40. We take the sum of those two things. So we take the square root of that sum. We get a number that's about 4.9. 30 degrees of freedom. We had our two sample sizes, 40 and 31. One less than the smaller is 30. And if we go to our table for T star with 30 degrees of freedom, we're going to use 2.04 for a 95% confidence interval. That's right down here. That's where that 2.404 comes from. So I'm going to ask you to go ahead and compute the 95% confidence interval, and we'll compare what you got to what I got when we get together in class, and you'll think about what your sentence of interpretation should be. Our hypotheses, is there a difference or not? Our null hypothesis is that there's no difference in the mean speeds driven by the men and the women. Our alternative hypothesis is that there is definitely going to be a difference. So again, I'm going to let you've got the summary data from favestats now. You can go ahead and compute the t-score, and you can use PTGC to find the p-value using the number of degrees of freedom that we talked about earlier. Write a sentence interpreting the p-value and make your decision. We will go over these results when you get to class. Just for comparison purposes, though, we can run t-test GC. Notice that since the data is preloaded, we don't have to enter the output of favestats here. We can just say it's going to be based on the variable fastest broken down by sex. Here's our data source, our null value, our two-sided, we tell it that it's a two-sided alternative. And as before, we're going to need to specify which group we're considering to be population 1. Here we chose it to be the men. So male is the entry for men in the sex column on M111 survey. So we put first equals male here. Again, I could include graph equals true if I wanted to include that graphical output. And so here's the output that you would get from running t-test GC. I'll ask you to go back and confirm that yourself. And you can compare this to the work that you did earlier. Again, you'll get slightly different things because you're going to be using a different number of degrees of freedom. And you'll see what you got for your conclusion, whether it would match with what we got here. And notice that instead of 30 degrees of freedom, our studio is using about 55.5 degrees of freedom. So again, I'll let you do the work by hand, compare it to this. Obviously, it will be slightly different because we're using a different number of degrees of freedom. but hopefully it won't be so drastically different that you should feel like you didn't get what you thought you should. And uh, we'll talk about this and see if you have any questions about it when we get together in class.